This is the Chapter 5 Part 1 commentary. In this commentary we're going to focus on summarizing the carboxylic acid key reactions. Going back to slide 5, as I circle in the upper side of the slide, here we see a carboxylic acid, and as previously discussed, if you sit there and you put this carboxylic acid inside water, then the carboxylic acid will act as a weak acid. That means the hydrogen highlighted in yellow will combine with a nearby solvent water molecule, where it will then form an H3O+, also called a hydronium ion. Now, as soon as it gives off its hydrogen, I'm going to go ahead and highlight the next step in green. As soon as it gives off the ion, it forms a carboxylate ion. This is unstable, and just as soon as it gave off its hydrogen, it could sit there and pick it right back up. So you can think of it as an Indian giver or a loan shark, where it then picks back up the hydrogen, forming the original carboxylic acid. So we call these reversible reactions because just as easy as it can go from the reactant to product, forming a carboxylic acid, it can change its mind and go the opposite route. Going to my ISIS examples in the very top example, which I'm highlighting. Here we have a carboxylic acid, also known as a butanoic acid. The hydrogen is going to come off and combine with a nearby solvent molecule. We go ahead and we write this in this form right here, H3O+, although if you wanted to, you could show 3 covalent bonds to each hydrogen. Either way, you can write the Lewis structure or you can write the molecular formula. Because the hydrogen left, this leaves this leftover carboxylate ion. I should point out, I could ask you to sketch this product, although I would not ask you to name it. I'm going to put this back, and let's go to the next example. In the lower portion of slide 5, we have our example, in this case benzoic acid, in water will give off its hydrogen, forming a benzoate ion and a hydronium ion. In slide 6, here is our second type of carboxylic acid reactions. So this is the second chemical property we're going to discuss. In this case right here, we have our carboxylic acid, which I'm going to circle, and we're going to combine it with a aqueous base, such as sodium hydroxide. Notice I said the word aqueous base. Even though it's not written here, actually the solvent is going to be water. So you can think of both carboxylic acid and sodium hydroxide being put in a beaker of water for this reaction to occur. Because we don't want to confuse you with the previous weak acid reaction, we tend not to show you that water as a solvent here, or write AQ for aqueous. So it's implied you're not responsible for writing anything with water, and we don't want to include it in there because we don't want to confuse you with the previous reaction. So let me go ahead and summarize the key parts. Just like last time, the hydrogen is going to come off, and then with a nearby sodium hydroxide molecule, the hydrogen and hydroxide are going to come together to form a brand new water molecule. The leftover carboxylate ion, which I'll circle in blue, is going to combine with the sodium. So these two are going to come together. Because we have a metal and a nonmetal, scientists often classify these as carboxylic acid salts. Now you're familiar with table salt, which is sodium and chlorine, or chloride, which is a metal and nonmetal. In this case, it's sodium and a hydrocarbon derivative. Nevertheless, scientists often simplify this also as salts. So make sure you're familiar with the term carboxylic acid salt. This is now going to be ionic forces, just FYI. And these are some of the strongest intermolecular forces. Stronger than hydrogen bonding, stronger than the dimer hydrogen bonding of a traditional acid. So it's at the top of the intermolecular force list. Here's a nice example. I could ask you to predict the product as well as name the product using the UPAC rules, which we learned earlier. So here we have acetic acid, aka ethanoic acid, 1-ethanoic acid using the UPAC name. The hydrogen and hydroxide come together forming the water. The leftover sodium in blue, underlined in blue, and the carboxylate ion will form this structure right here. The common name for this one is sodium acetate. The UPAC name on this one is going to be sodium ethanoate. Sodium ethanoate. So let me go ahead and write that underneath. So the common name for this one would be the UPAC name for this one would be sodium ethanoate. So this is the UPAC name. The top one is the common name. You'll be responsible for the UPAC name. The next one is benzoic acid. Again, the hydrogen hydroxide come together, forming water, and then you have your leftover potassium and your benzoate ion, and they form potassium benzoate. By the way, this name right here is the UPAC name, and it's something you should be familiar with. Potassium benzoate is actually sodium benzoate, using the other metal sodium, is actually a very, very common preservative. It's known for actually upsetting the reproductive system of bacteria, causes them to go sterile. So I think it's called hemostatic. Forget the name hemostatic. I'm thinking of something else. Let's move on while we still can. So bottom line is it's a preservative, and that's all I'm going to say about that one. So let's go to my examples in the ISIS draw. So carboxylic acid formation. I do want to point out that this is often how we make soaps. We have these really long hydrocarbon tail acids, and by adding in something like sodium hydroxide or potassium hydroxide, we can make these soap molecules. Hence, the other name for this is saponification. Pronounced saponification, I say saponification. Tomato, tomato, sapon, sapan. Start off with hydrogen, and we combine it with the hydroxide from sodium hydroxide, and this goes ahead and creates, and I'll highlight it right here, this creates our water molecule. The leftover carboxylate ion will will combine with sodium, leaving this structure right here. I do want to point out that when it comes to using the little autonom system to name it, it doesn't work right. It actually uses an older UPAC naming scheme for it. Furthermore, naming it with salts is really hard. It has trouble identifying it. So you will have to name it using the rules listed out in the slides and commentary. But FYI, the name for this one is sodium. And then 1, 2, 3, 4. 3 chloro bute and OIT. Don't want to get the benzene and the butane confused. Butane OIT. Sodium 3-chloro-butane OIT. Notice, even though it has a functional group chlorine on there, it's just window dressing. It has no actual effect on the reaction. So you'll notice I try to include those quite a bit. I'll have these branches or extra functional groups that have nothing to do with the reaction, just to make it more realistic. As we often have this in nature, we'll have multiple functional groups, and only reactions that we study focus on one particular functional group and not the others. So in my next example over here, I have an ether functional group on there, and here I have a branch. Although it's not a functional group, it can still throw you off the track. So if I give you the starting reactants, you'll be expected to predict the product. So in this saponification product, just like last time, the hydrogen and hydroxide come together, forming the brand new water molecule, and then you have a isopropyl on the bottom, which does nothing. You have an ether on the bottom, which does nothing. The leftover carboxylate ion will combine with sodium, forming, and let me go ahead and write this right here, forming sodium space, and then this is going to be 2-isopropyl 3-methoxy 1, 2, 3, 4 butane OIT. Make sure you have a space between the sodium and make sure you have a space between the sodium and the rest of the parent, so that way I can identify that these prefix branch names are on the carboxylic acid parent. Let's go to the next one. In this case, we start off with benzoic acid, and we're going to go ahead and form sodium benzoate. For this class, don't worry about capitalizing. You can have them all caps, you can have none of them capped. That's okay. Alright, let's move on. Our last topic is going to be esterification. So, it's going to be the same type of process. Instead of swapping out, however, the hydrogen with a sodium, we're going to be swapping out a hydrogen with a alcohol. So in this case, and I'll highlight everything in blue, or I'll circle it in blue. So in this case, the alcohol portion of the carboxylic acid and a hydrogen from another alcohol or phenol in the presence of a acid catalyst along with a lot of along with a high temperature. It's going to form a brand new water molecule, and then the remaining components are going to form what we now call a carboxylic ester. So this is a carboxylic ester. The brand new carbon, oxygen, and then carbon is now called a ester linkage. An ester linkage. So this right here is called a ester linkage. If you notice, it looks very similar to a ether reaction. So pretending we don't have this carbonyl right here, again, in an ether reaction, we'd swap out the hydrogen and hydroxide, forming water, and then we'd have a R single bond O single bond R. So it's very similar to an ether reaction, only there's a carbonyl present, so we call this a carboxylic ester. Carboxylic ester. There are various there are various names to it, so different names for the same thing. Some people call this carboxylic acid ester. Other people just refer to this as a ester by itself. The key word on this one is ester. Ester. Now, the process of making an ester is called, cleverly, esterification. So let's go to a couple examples. Here we have butanoic acid and we have an alcohol. So it always requires an acid and an alcohol. The hydrogen hydroxide form a brand new water molecule, and then the leftover oxygen forms a brand new ester linkage known as a carboxylic ester. Here we see anti-acne medication called salicylic acid from the salix tree, or salix tree. That's where they get the name, salicylic. And again, hydroxide hydrogen form a brand new water molecule, and then the leftover oxygen and carbon form a ester linkage. Salicylic acid is a very popular medicinal molecule. So in this case, it'll sit there and can be the precursor for a breath freshener, or if you were to sit there and add a different molecule, I could sit there and turn it into acetylsalicylic acid. So salicylic acid is a very popular precursor for making a lot of popular medicinal related drugs. Let's go to my ISIS to finish this up. First off, we need the catalyst, sulfuric acid, and heat. If you say acid, or if I say acid, or if I just say H+, it's all the same thing. So in this case, the hydrogen and the hydroxide are going to come together. Hydrogen from the acid, hydroxide from the alcohol molecule. And then they're going to go ahead and form a brand new, what I'm highlighting to the right, water molecule. As far as the rest goes, the minute the alcohol and hydrogen is removed and the hydrogen is moved on the other, then the remaining part forms a brand new ester linkage, and this is now a carboxylic acid ester. Again, the auto naming system in the program doesn't work right for these. They actually use a older generation naming scheme which is not acceptable for this class. So use the naming scheme on the slides and the commentary. In this case right here, we're going to put the alcohol portion of the name first as its own unique prefix. So in this case, we go ahead and we start counting from the carbon which is directly attached to the original alcohol of the carboxyl group. So the single bonded oxygen. So in this case, this will be carbon 1, carbon 2, carbon 3, and carbon 4. So it's going to have the initial name butyl. You put a giant space in between that says that's connected to the single bond oxygen. The rest of this will be to the parent carboxyl group. So in this case, this would be butyl benzoate. Benzoate. Keep in mind for esters, it's always going to have the oate to it. Let's go to the next example down here. Again, the hydrogen hydroxide are going to come together. Hydrogen from the acid, hydroxide from the alcohol, forming a brand new water molecule you see on the lower right hand side. The leftover carboxylate anion and the leftover hydrocarbon is going to form a brand new ester. Keep in mind, the rest of the functional groups or branches are just window dressing. They have no actual function in this particular reaction. They're just there to throw you off. So in this case right here, the proper name for this one, starting with the single bonded oxygen and its alcohol group, would be 1, 2, 3, 4, butyl, giant space, and then the rest of this. So in this case, carbon 1, 2, 3, 4. Parent is 4 carbons. On carbon 2 there's going to be an iso. So 2 isopropyl. 3 methoxy. And then butanoate. So this concludes the this portion for the Chapter 5 Part 1 reactions.